Welcome to today's webinar on assessing the capacity of natural features and subsurface geology for carbon sequestration. This is a new area for us and consistent with our theme of sharing our lessons, our projects that we have done and affiliations that we've made. We are bringing the lessons we've learned and the stories we can tell to you to help our broader community function in the broader practice of the work they do. As many of you know, Canada is implementing a strict regulatory framework to reduce greenhouse gas emissions to between 40 and 45% below 2005 levels by 2050. And most provinces are following through on their own mandates. And this is something that we learned, is that natural features is a significant part of the sequestration story of offsetting our carbon emissions, notably through surface features and subsurface features. And we've got two speakers speaking today that are specialists in those respective areas. So the areas that we are going to be covering include natural features such as agriculture, forest, peat bog, foreshore, grassland, and subsurface geology, notably sandstones and coal, both of which have a significant capacity to sequester and store carbon emissions, which in turn mitigates the impact of land and industrial impact on carbon emissions. So our study helped identify how these land management strategies could maintain and improve the sequestration in that regional district. And it also outlined a process where they can incorporate those findings into their land management processes. So with that, I'm going to move to introduce our speakers. We have three speakers today. Our first speaker is Professor Shaheen Gashgard, calling in from Burnaby, BC, near me in Vancouver, who is Nurse Sciences Professor at Simon Fraser University in BC. Shaheen has authored or co-authored over 100 publications, including multiple papers related to subsurface CO2 sequestration. He was awarded the James Lee Wilson Award from the Society of Sedimentary Geology in 2012 and the Link Award from the Canadian Association of Energy Geoscientists in 2013. He's currently working with the BC Ministry of Energy and Climate Solutions to assess the potential for CO2 sequestration below both Vancouver and Vancouver Island. He's a professional geoscientist with Engineers and Geoscientists BC. In lieu of a fee for today's presentation, Shaheen has kindly made a donation to the Musson Creek Fish Hatchery, part of the Burrard Inlet Marine Enhancement Society in Lower Mainland BC. So thank you for that generous donation, Shaheen. Second speaker, Professor Maria Strack, Professor and Canada Research Chair, Geography and Environmental Management at the University of Waterloo. Professor Strack's research focuses on peatland greenhouse gas fluxes in both natural and disturbed ecosystems. She collaborates on several peatland restoration projects across Canada, including restoration of sites used for horticultural peat extraction, former well pads and roads related to oil extraction and peatland construction in oil sands in mining regions. Her interest is in evaluating the conditions that help to return a carbon accumulation function post-restoration. In lieu of a fee today, Maria has made a donation to the Rare Charitable Research Reserve, a community-based land trust and environmental institute dedicated to protecting over 1,500 acres of environmentally sensitive land across Waterloo Region and Wellington County in Ontario. And our last speaker is Mr. Brennan Anstey, who is the Operations Manager for Environmental Science, Emissions Reduction and Compliance at Pinchin, based in Vancouver. He manages our Natural Sciences, Environmental Engineering and Environmental Assessment Group, and he's also a professional engineer with Engineers and Geoscientists BC. So with that, I'd like to pass the lectern over to Shaheen to begin the presentation. Thank you very much.
Thanks, John, for that. Good morning, everybody. Just wait for these slides to pop up for me, and then I'll get started on this. I'm going to be talking today about the really a quick overview of how we capture industrial carbon and sequester in the subsurface. It also applies to air capture of carbon, because this is one of the technologies that's actually readily implementable today. Now I'm seeing if I can move forward on the slides. I don't seem to be able to. Oh, there we go. So we're really looking at the whys and hows of how we capture and store carbon underground. And when we talk about this, we're really talking about a three-stage process. So we're not dealing with natural carbon in the atmosphere. We're largely focusing on industrial sources because that's actually an enriched form of carbon dioxide and some of the easiest stuff for us to capture. As well, industrial carbon is outside of the biological carbon cycle, and so it's an additional element that's being added to the cycle. And so it's one of the things that's contributing most to global warming. So when we think about carbon capture and storage, we're thinking about it in a three-step process. There's the capture part, the transport part, and then the storage part. Now, this diagram actually shows the overall carbon cycle, and you can see there's many different elements of carbon in the biosphere and cryosphere and hydrosphere, but we're really dealing with the industrial element of that. And so the average CO2 concentration in the atmosphere is about 0.04%. The average CO2 concentration in smokestacks is anywhere from 4 to 20%. And so capturing that CO2 makes the most sense for us because it's going to have the highest impact for reducing overall emissions. Now, the way it's done in today's world is using a chemical process, an amine process. And so they basically put the smoke from the stack through a chemical process. They strip out the CO2, and then they extract the CO2 from the amine. Well, over time, that chemical breaks down, and then they have to dispose of it. And unfortunately, it's a cancer-causing chemical. So it's not the best process or most environmentally friendly process that's out there, but there is a lot of work being done to try to improve on that process. And this is a plug for a Canadian company based here in Vancouver called Savante. They've actually been developing a machine that actually uses filters and captures about 99% of the CO2 from smokestacks. So their systems are actually quite economic. They're quite useful. There's not a lot of them deployed right now. I think there's actually one at present that's in use. So you need about 55,000 of these to capture the 40 billion tons of industrial CO2 that's out there. So we're looking at a fairly major ramp up in order to address the industrial CO2 problem, but we are at the starting phases for capturing that and reducing it. Now, once you capture the CO2, you need to do something with it. Well, first you need to transport it. And there's many different ways for transport. People have looked at transporting by rail, transporting by truck. By far and away, the most economic and the safest way is to transport it by pipeline. And if you're looking across Canada, the two provinces that are really at the forefront of this are Alberta and Saskatchewan. Saskatchewan's had one of the longest running CO2 projects at Weyburn, but that's for enhanced oil recovery. In Alberta, they have Quest and there's a number of other projects that are starting up. There's also a lot of talk about the Pathways Alliance to bring CO2 from the oil sands down to east central Alberta. So those pipelines allow the movement of large volumes of CO2 in a safe manner, and that's something that's being considered as well. What we're going to focus on, however, is actually what happens when we have that CO2. So we've captured it off the smokestacks, we've transported it to our site, and then what actually happens to it. And that's where we start to look at injecting that underground and what happens to the CO2 once it's injected underground. And there's a whole different array of places you can store this. As John mentioned, sandstone and coal are two elements. The other is in basalt. We're going to look at sandstone and basalt in a little bit more detail because those are the two most advanced forms of subsurface sequestration that are being done at present. So how does this work? Well, if you were to take CO2 and look at the atmosphere, take a volume of 100, and we're not going to give it any units, just call it 100. Once we take that volume of 100 and we take it down to about 800 meters depth, we actually compress it to about 0.3, so a 300 times compression of that CO2. And that's when the CO2 transitions from being a gas into what we call a supercritical fluid. And a supercritical fluid basically has the density of a fluid, but the viscosity of a gas. So it's actually able to, viscosity of water but a lower density. So we're able to then inject that underground in large volumes because the same amount of gas in the atmosphere then occupies a much smaller space in the subsurface. So it becomes economic from the perspective that we're not needing as much volume to actually remove that CO2 from the atmosphere. So we're looking for injection sites that are in rocks that will have the space to absorb that CO2, but are below about 800 meters depth. Now, there's two different types of rocks, as I was mentioned, that we're discussing, and depending on the rock we inject into, the CO2 is going to react differently. So we're going to go through both of these two elements here. On the left, you're seeing what would happen if we injected into sandstone or carbonates, and then on the right is what you would expect to see if you're injecting into basalt. And the only difference between this is the reactivity of CO2 that's dissolved in water, where it forms an acid, with the rock and actually what actually happens to that CO2 water mixture and rock and the reactions that happen therein. So we'll start with sandstone, a sandstone example, and then move on to the basalt. So for those of you that aren't familiar with oil and gas extraction, oil and gas is extracted from the subsurface. It's not actually extracted from large caverns. It's extracted from the pore spaces between grains of sand. So if you went to any beach or any river and you saw sand accumulating in those environments, once they get buried, they get lithified, so turned into rock. And the pore spaces, the holes between those grains of sand, is actually where oil and gas is stored. So when we extract that oil and gas, that pore space then becomes available for the injection of CO2. As well, the size of the connections between the pore spaces determines what's called the permeability, and that's actually the injection rate. So the more porous, the larger the number of holes, and the more permeable the rock, the ability to inject into it, the better that rock is for sequestration. And a lot of different parts of the world, actually, and parts of Canada, our major cities, overlie sedimentary rocks, not just on the prairies, but also in the southern Ontario region and also in lower mainland of British Columbia. So this is this picture here on the left-hand side. That's a picture of a core. So that was taken about 1,200 meters under the ground in Vancouver. And you can see orange, uncolored rock, and then green. The uncolored rock being the red labeling at the top. That's the finer the grain size, the more muddy the rock is, the worse it is for CO2 sequestration. The more porous and permeable it is, the more sandy and gravelly it is, the better it is for sequestration. So we can actually map those out, predict their architectures of those rock types, and then determine what volume we can actually inject underground. And so in the Vancouver region, we have rock that's porous and permeable to about 2,000 meters depth. If you were to go to different parts of Alberta, you could go down to about 4 or 5 kilometers in those regions. So what are we doing here in BC? Well, we're using different information that's available. So seismic lines, that's the picture on the right. Those are seismic lines that are taken below the lower mainland. We map out different horizons. We tie that into the different rock types, and we start to map out the volume of rock that's available for sequestration. And then we propose sites where we could inject or theoretically inject CO2 for the long-term storage of that rock. Now, once that CO2 is injected underground, it comes in as a plume. So we have an injection well here. It injects our CO2 underground in a supercritical state. That CO2 actually has a lower density than water, so it will actually migrate up through that porous and permeable rock until it's trapped below an impermeable rock. So think of the permeable rock like sandstone, and the impermeable rock is mudstone. And so we map out the architectures of those, and we can predict where the CO2 is going to accumulate. That trapping below an impermeable rock, we would call structural stratigraphic trapping. That has the highest volume, the highest capacity for storing CO2. Once that CO2 dissolves with water, it then reacts with minerals in the rock and it turns into carbonate material. And that then binds it in a mineral form, which has a long-term potential for safe storage over a very long period of time. And the mineral trapping capacity of the formation is going to be determined by what the makeup of the sandstone is. So there's less capacity in sandstone for mineral trapping, but more capacity for structural and stratigraphic trapping. One of the biggest places where they're doing this is in Norway, offshore Norway, at the Sleipner field. Sleipner is a gas. They produce gas, natural gas from that field. It also is rich in CO2. They strip the CO2 off the gas plume that's being extracted, and they inject it back underground. And they've been doing this since about 1996. And what's really nice about this project is all of the data that they've collected from it has been made publicly available. So it's allowing a lot of people to use that data to understand the long-term impacts of CO2 sequestration. They've sequestered about 16 million tons per date. just to give you perspective, to go back to the annual global production, it's about 40 to 50 billion tons of industrial CO2. So we would need a lot of Schleipners to actually meet reduce the overall CO2 sequestration of industrial CO2. What happens to that CO2 when we inject it underground? Well, of course, it migrates up, and this is an example of what it looks like. If there's any breaks in the overlying mudstone, the CO2 will migrate through that until it hits the next stratigraphic break. And so there's a lot of work being done by geologists and engineers looking at CO2 sequestration projects, trying to determine what the long-term, what volume and injection rate we can inject CO2 at, and what the long-term stability or safety of that injected CO2 is based on chances of leakage to surface. And so we're looking at 5,000-year timeframes. That's the ideal to sequester that in the subsurface. Now, the other element that we actually have, or the other rock type that we can look at, is sequestering into basalt. And this isn't really a huge option across most of Canada. It is an option here in southwest British Columbia because we're in a tectonically active region with a lot of volcanism. And so Canada is actually, I guess, blessed with a limited number of volcanoes, except here on the west coast, where we have a series of these. And so injecting into basalt still requires porosity. It still requires permeability to inject that CO2, but there's a much faster mineral reaction in this case. So the place where this is being done the most is actually in Iceland at a place called Carbfix. There's a power plant there that produces about 12,000 tons of CO2 annually. That is then injected underground where it's mixed with water within the wellbore and then injected into porous and permeable basalt. And so in that case, it's an igneous rock, but it had a lot of trapped gases. Those trapped gases leave holes in the rock, which are very well connected. And then we can inject CO2 into those spaces. And so in this case with the Carbfix, they're seeing 95% mineral fixing of CO2 in under 2 years, which is actually incredibly fast. We're basically injecting industrial CO2 and then having it form rock right away. And if you look at that picture in the lower left or lower right, you'll see that white material, that is actually carbonate material. That's CO2 that's reacted with basalt. Basalt's rich in iron and magnesium, and those minerals break down rapidly when exposed to an acid, and then they form into a carbonate rock. So that's a fairly promising thing, just a limited application here on the west in Canada. In the case of the Carbfix example, the benefit of that is that the injection well is very, very close to the power plant. So the costs for capture, transport, and injection are relatively low. They can do it for, well, about $30 a ton. That's incredible, really. We don't really have those options here in Canada because of we need much longer transport distances, and monitoring would be much more of an issue. And so just to give you an example, this is what's being done. They're looking at this off the west coast of Canada. The idea would be to build a stainless steel pipeline through the Strait of Juan de Fuca out into the middle of the ocean, and then inject into porous basalt out there. That would be incredibly expensive. The other would be to build a ship that can then capture CO2 directly from the atmosphere and then sequester that CO2 directly below the ship. Again, the problem with that is that we're trying to capture very low concentrations of CO2, 0.04% of atmospheric CO2, and then injecting it underground. So again, it's the cost of that is very, very prohibitive. So really capturing industrial carbon and sequestering that into sandstone reservoirs is the most promising, especially in the Canadian context, and it's being looked at in a number of places across the country. So just to kind of summarize all of that, we're looking at subsurface disposal being the fastest and most economical way for getting rid of CO2, especially abiogenic or industrial source CO2. So it would be the fastest and most reliable way to address climate change right now. We would need to inject into porous and permeable rock, and depending on the type of rock, we would inject at different depths. In sandstone, where we rely on structural and stratigraphic trapping, we want to be below about 800 meters depth, where we inject in a supercritical state. In basalt, we're looking for the mineral trapping capacity, so we still need porous and permeable basalt, but we're looking for the reaction between that CO2 and the rock to form a mineralized carbonate. So with that, I will say thank you, and pass it along.
Thanks, Shaheen. And oh, no, slides disappeared for me, so I'm not sure what happened there, Aaron. Okay. Do you want me to go ahead and take control, Aaron?
Yeah, you should be good to go now, Maria.
Okay. Great. So we're going to switch gears a little bit here and move the focus from storing carbon underground to talk about the potential for natural features to store carbon. And specifically, I'm going to focus on wetlands, but I will provide a bit of an overview of the potential for nature in climate mitigation. And just before I start, I do want to acknowledge that I'm speaking to you today from Waterloo. Waterloo sits on the Haldeman Track, which is 10 kilometers on either side of the Grand River that was promised to the Six Nations, and is also the traditional territories of the Attawandaron, Anishinaabeg, and Haudenosaunee people. So I feel really blessed to be able to live and work and play on these lands and to experience a lot of the wetlands here. And the work that I'm sharing today has really been a team effort led by many of my graduate students and research partners. I want to acknowledge the funding sources that have funded the work I'm going to talk about today. And then I put there some of the collaborators whose work that I will be featuring today. So I'm going to spend about the next 15-20 minutes with you to provide a bit of an introduction to nature-based climate solutions largely and their potential in climate action, and then end with a case study specifically about wetlands and how we can think about managing them from a climate action perspective when we think about urbanization and suburban development. So when we talk about nature-based solutions, it might be sort of a buzzword of today, but it actually is a concept that we've thought about for decades when we think about ecosystem services and the potential for nature to provide societal benefits. But it wasn't until about 10 years ago that the International Union for the Conservation of Nature wrote a guide specifically about nature-based solutions where they put forth the definition that I have on the slide here, which are that nature-based solutions are actions that protect, sustainably manage, and restore natural and modified ecosystems in ways that address societal challenges effectively and adaptively that provide for both human well-being and biodiversity benefits. So that's a really key aspect that we're thinking about, addressing societal challenges, but that it also should be inherently good for nature itself and the other organisms that use that space. And these can be addressing a whole range of challenges as sort of shown in the image here, but our focus today is going to be on what's sometimes called nature-based climate solutions or natural climate solutions. And we can think about those in terms of climate change adaptation. So how can nature be used to help us avoid some of the impacts that climate change might have? So for example, wetlands along coastal areas to prevent the impacts of storm surges or flooding. But what I'm going to focus on today is natural climate solutions in terms of mitigation. So how do we actually reduce greenhouse gas emissions or keep more carbon on the landscape? So when we talk about natural climate solutions in that way, we're thinking about how can we reduce emissions of greenhouse gases from land use and land use change? How can we use intact ecosystems to capture and store additional carbon dioxide from the atmosphere? How can we improve ecosystem resilience so that they'll continue to do that job moving forward? And there's many different ways that we can do that work. About forestry, and you hear a lot about planting more trees, but this could also be related to changes in agricultural management or the management of wetlands, which will be the focus today. And so close to 10 years ago now, researchers around the world got together to try to calculate what is the potential of nature in climate action and to reduce greenhouse gas emissions. And that's the paper I'm showing here. And they determined that the maximum potential for natural climate solutions in 2030 was about 24 petagrams, or petagrams the same as billion tons, gigatons of carbon dioxide equivalents per year. And putting that into the perspective of the greenhouse gas emissions reductions that we need, that those natural climate solutions could provide just over a third of the cost-effective climate mitigation that was needed through 2030. So this highlights that natural climate solutions can be a key tool in our toolbox, particularly in the short term, but that they're not going to provide all of the climate action we need. So this really highlights like the importance of what Shaheen was talking about exploring other mechanisms to reduce our greenhouse gas emissions, and that nature then could play an important role in the near term while we make that transition and rapidly reduce fossil fuel emissions. If we think about this from a Canadian context, nature has also been recognized in, this is a report from the Canadian Climate Institute, looking at strategies to reach Canada's net zero goals. First, the goals in large reductions to 2030 and then to net zero in 2050. And I've just highlighted in green there land use, which is those natural climate solutions. In 2030, they're sort of one of the largest circles, which the circle size is like the potential greenhouse gas emission reductions. And they remain still a dominant, like large size of circle to 2050. But they were placed in this report in what was called the wild card opportunities, because there's still a lot of unknowns in the actual potential to apply these solutions on the landscape. What would be the uptake and the actual area that they could be applied? And then what are the greenhouse gas emission reductions that we would actually achieve? And so that's actually what a lot of my research program is about. From a wetland perspective, how can we reduce those uncertainties and better understand the potential of wetland management to contribute to climate action? So here, I'll sort of move forward to just talk and introduce a little bit about wetlands and peatlands. Just so that we're all on the same page, I always like to start with a wetland definition, and this comes from the National Wetland Working Group's Canadian system for wetland classification. And they define wetlands as land that's saturated with water long enough to promote wetland or aquatic processes, and that looks like poorly drained soils, hydrophytic or water-loving vegetation, and biological processes that are characteristic of wet environments. So basically, they're saying that wetlands are land that is wet. And we give them a lot of different names on the landscape, some of which I've listed here. In Canada, many of our wetlands are peatlands, where we're seeing that one of the biological processes that are characteristic of wet environments is very slow decomposition rates. So when organic matter is deposited in the soil in a wet condition, there's very little oxygen available for decomposition, and that organic material accumulates. And when we've accumulated over 40 centimeters of a largely organic deposit, then we consider that wetland to be a peatland. And over 90% of the wetlands in Canada are peatlands. So this is sort of the vast majority of our wetland ecosystems in the country. And I just have a picture there of sort of that peat deposit. And so when we think about the potential for wetlands to contribute to climate action, we have to think about that carbon storage, but they also exchange other greenhouse gases that we need to take into consideration. And so this is just a bit of a wetland greenhouse gas exchange 101 to sort of put that into perspective. So we already know that they're storing all this carbon, and that's because through photosynthesis, the plants are taking up CO2, but then most of that is being stored in the soil in the long term and not being back released to the atmosphere. And so we know then that wetlands are these long-term sinks of carbon, and predominantly that means they're net sinks of carbon dioxide. But that wet soil that slows decomposition leads to other, has very low oxygen and leads to other processes that can produce small molecules that move around with the water called DOC, which has impacts for downstream ecosystems, but largely contributes to carbon dioxide losses. And it also leads to the lands are also globally important sources of both methane and dissolved organic carbon. Wetlands can sometimes also produce the greenhouse gas nitrous oxide, but in a natural state, this tends to be negligible. However, when we have a nutrient-rich wetland that has been drained, or when there's a lot of nitrogen sources like fertilizer has been applied in an agricultural setting, we can have substantial nitrous oxide emissions that we should consider in our greenhouse gas budgets. But when we put all of this together, we know that an undisturbed wetland generally has a net climate cooling effect. The emissions of methane and nitrous oxide are more than offset by the uptake of carbon dioxide and its long-term storage in those soils. And this is good from a Canadian perspective because we have a lot of wetlands. We're a country that is rich in wetland area, and I'm just showing here the proportion of the landscape covered by wetlands. On average across the country, they cover about 13% of the land area, and Canada has about 20% of the world's wetlands and a quarter of all the world's peatlands. And they're largely in an intact state. We have lost a lot of peatlands in southern areas, and particularly in southern Ontario, where I live here. But across most of the country, wetlands are intact. And that means we have an incredible amount of carbon stored in these wetlands. We estimate that 150 to 160 billion tons of carbon are stored in current wetlands. To put that in perspective, if this was emitted to the atmosphere, it would be equivalent to over 800 years of Canada's current anthropogenic greenhouse gas emissions. So this is an incredibly large pool of carbon that's worth protecting. So how do we then manage these systems for nature-based solutions, or we could also just say in climate-friendly management options? Well, we know that in a natural state, they're a net sink for carbon and tend to have that cooling effect, but disturbance exposes that stored carbon to decomposition. It might make them more prone to things like wildfire. And so we can just avoid that disturbance or reduce the amount of disturbance on the landscape and protect that carbon in place. In areas where we do have a lot of disturbed or degraded ecosystems, we could move towards ecological restoration to start to return those ecosystem functions of carbon storage. So we should do more restoration and do it in the best way possible. So a couple of years ago, scientists in Canada got together, and I was able to be part of this group with myself focusing on the wetland side, but we aimed to try to understand what was the potential in Canada of all of our ecosystems to contribute to climate action. And we came up with a number of about 78 megatons of carbon dioxide equivalents that could be reduced in the year 2030. This is equivalent to the emissions of powering every home in Canada for about 3 years. But Canada's emissions are currently around 700 megatons, so this is only a little over 10% of what we would need to meet net zero. Again, highlighting that nature is an important tool, but not the only tool that we need for climate action. And we thought very broadly about many different types of management on the landscape. And agriculture was the largest opportunity, improving agricultural practices for reducing greenhouse gas emissions. But wetland management accounted for about 20% of that 2030 opportunity, and even more sort of as we looked into future decades. And what I want to highlight here is that the most important actions that we could take that led to the greatest greenhouse gas emission reductions were from avoiding future disturbance, both to peatlands and freshwater mineral wetlands. And this is for a couple of reasons. Firstly, when you avoid disturbance, you get immediate benefit. You automatically keep that carbon in the soil and out of the atmosphere. But secondly, the vast majority of Canadian wetlands are intact. So we just have a lot more area where we can protect and avoid conversion than we do for restoration in many cases. So with that in mind, I just wanted to walk through one example of some of our recent work thinking about wetlands and their carbon storage in Southern Ontario. The wetlands that remain in Southern Ontario are now predominantly swamps. These are forested wetland ecosystems, which can be wet and flooded, like in this image that I'm showing here for parts of the year, but are often also quite dry in other parts of the year. So often you may just think of it as a beautiful temperate forest that you're walking through. Swamps were not always the most dominant peatland in wetland in Southern Ontario, but many marshes have been lost to agricultural drainage, making swamps now the most important wetland type. And one of my PhD students, Meg Schmidt, has been doing a lot of work trying to quantify how much carbon is stored in these ecosystems and what are their greenhouse gas exchanges. And so working across 12 sites across Southern Ontario, Meg has come up with values of about 16 kilograms of carbon per meter squared being stored in the forest biomass, but then, 3 times that being stored in the soil carbon stocks. This is about double what we have in temperate forests that are not swamps in Southern Ontario, really highlighting the potential of those wet soils to store more organic matter. And so these systems are almost like the Goldilocks of carbon storage, because we get lots of carbon still stored in the overstory trees, but even more carbon stored in the soils than we would in an upland forest. And because these swamps are often dry for a large part of the year, they do this carbon storage by still, in most cases, having low methane emissions. So on the left, I'm showing here all the methane measurements that were made across those 12 sites. And aside from 2 sites, all the sites actually were net sinks or taking up methane from the atmosphere. And compiling data on nitrous oxide across those sites, we also see low emissions and actually a sink most of the time for nitrous oxide. So we're really seeing that potential for climate cooling in these swamp ecosystems. But as we continue to have development in Southern Ontario, we often see a loss of these wetlands replaced by more engineered blue-green infrastructure like stormwater management ponds. And we see this looking at some land use change data that was compiled by a PhD student with one of my colleagues a few years ago, looking at wetland loss and stormwater pond gain from 2002 to 2010 across several municipalities in Southern Ontario. And if you look at sort of the combined total there, you can see an almost 1-to-1 loss of wetland area and replacement with stormwater management ponds. And so we wanted to understand whether these stormwater management ponds were also providing some of that climate regulation function that we were seeing in natural wetlands. This is some work from a project on municipal planning that's funded by Environment and Climate Change Canada, and the work of my former master's student, Akshara Withanagay, who went around to 24 ponds in the Waterloo region and measured their greenhouse gas emissions with floating chambers like you see in the picture here. And what Akshara found was, at least in the open water area of those ponds, instead of taking up greenhouse gases, they were releasing carbon dioxide, large amounts of methane, and were almost neutral for nitrous oxide. So if we think of the greenhouse gas balance of those systems, it was predominantly a source because of these large methane emissions that we're seeing. Now, there could be carbon stored in the sediment, but we don't really consider that a long-term carbon storage in these systems because they're often dredged so that they can maintain their flood mitigation potential. But we are doing some work on the carbon stocks in those systems. Where there may be some carbon storage potential is in the riparian vegetation around those ponds. And we're just finishing up a project now where we've done a lot of harvesting to quantify those carbon stocks and are working with remote sensors on how we can develop methods to monitor those with drone imagery. So just a few take-home messages. Despite many historical wetland losses in southern regions, Canada is still a global powerhouse for wetland area and carbon storage in those wetlands. When we think about what we should, how we should manage that carbon stock, avoiding wetland conversion, we know protects those stocks and is really the biggest opportunity for greenhouse gas emission reductions over the next decade and into the near future. And when we think about urban and suburban development, replacing existing wetlands with constructed systems does provide key ecosystem services like flood mitigation, but likely not climate regulation benefits. And with that, I will pass it on.
Awesome, thank you. Those are great. All right, so we're going to shift gears a little bit. This is the last segment of the presentation, then we'll do questions. So I'm going to talk about a project where we quantified the carbon sequestration in order to help our client basically make land management decisions. So our work is largely based off of research similar to the research that we just heard about. And so I will walk you through what the project was, what kind of questions they were asking, and what we found out. All right. So this project, it was we won it on an open public bid. It was put out by the Comox Valley Regional District. It's a regional district on Vancouver Island, floating in the Pacific Ocean, just off the coast of BC. So and it was a really interesting proposal to read. Their key question was they wanted to know how they can best manage their land to sequester the most carbon. So I'll repeat the question because I had to read it a number of times when we were putting together our bid. They wanted to know how can they best manage their land to sequester the most carbon, and where it's coming from is they had done, like many municipalities, they had done their emissions inventory, so they kind of had a sense of what their emissions were, but they didn't have a good sense of. They said, okay, well, like we have all this land, it's full of trees, different ecosystems. It must be sequestering carbon. Does that can we add some minuses to our ledger here? Like we know what emissions we're producing, but we don't know what minuses, and can we increase those minuses if we manage our land slightly differently? So that's kind of where they're coming from. Provincially, both BC and Ontario have requirements for municipalities to meet emissions targets. So they're working on doing this, and they wanted to see if natural systems can play a role there. So these are the steps that we took to try and answer those questions. We started with mapping sort of what kind of natural ecosystems do we have and how much. That's our mapping project. And then we looked at factors affecting biological carbon storage. We essentially had to help them understand, like, okay, in your main ecosystem types, here is how carbon works. Like, here's how it gets sequestered, here's how it gets released, and put numbers to it. Then once we had that, we said, okay, we kind of know what you have. We know whether it's sequestering or not sequestering carbon. Here are some levers that you can pull to get things to sequester more carbon. And finally, one that kind of snuck up on us is we also looked at stored carbon. Like Maria was talking about, the more organic carbon, like in wetlands, it's stored in, a lot of it is stored in like peatland. How does that play into the whole balance of like carbon's emitting, carbon not emitting. And then we kind of brought it all together into a model to say, okay, well, if you do this, this will happen. If you do that, that'll happen, to help them understand what they can and cannot do. So, so this is the map that we produced for them, or kind of like a slice of the map, showing the different types of ecosystems that they had in the region. So we color coded them, different color for different ecosystem. I believe brown is forest, so most of the region was forest. And then we kind of broke it down into hectares, as well as like a percent area, so you can see. I mean, aquatic blue was a big one because that was their, I guess, chunk of the ocean. But forest, which we broke down into actually 3 groups: stable, regeneration, and old growth, kind of like younger, medium, mature, and really old forest, to kind of get a sense of how much of each they had, because they had quite significant, different sequestration rates. So we wanted to break them down a bit. But that was over half of the region. So anyways, we mapped it out, and it's important to know how much of what they had, because it wasn't just about which ecosystems sequesters the most carbon, but it was a combination of which ecosystem sequesters the most carbon and how much of that ecosystem do you actually have. So the focus areas for the assessment, we looked at baseline carbon sequestered. So for that ecosystem, the way it normally presents in the region, how much carbon is it sequestering? And we looked at kind of like an annual basis, because sometimes at different times of the year it may be emitting and then maybe it's sequestering, but overall, what's it doing on an annual basis? Then we looked at different land management options to optimize carbon sequestration, like what levers can you pull, what can you do differently to get it to sequester more. And then we also looked at embodied carbon, like, okay, how much is there now? And, what happens with, what could happen if you lose that? Like Maria was talking about, if the wetlands are lost, that's a lot of carbon that is being released all at once. So we wanted to get a handle on that, so we really understood what was going on. So this is, not expecting you to read all these numbers, but this is sort of like a condensed version of our model, and it gives you kind of the main building blocks for how we did it. So in green, we have the areas. So we're quantifying how much land, which different ecosystems we have, and how much of them we have. So again, we characterize the hectares and area percent. That's basically the same table that I showed you with the map, with the green header. And then the exciting part, we looked at, okay, how much, on average, how much carbon are we sequestering? And we ended up looking at it in 2 different ways, both in carbon dioxide equivalents, but also just as carbon. And that was important when we looked at stored carbon, because you don't actually store CO2 in this case, you store it as carbon. It's a simple conversion, so we had both numbers there just to make the model work. And then we looked at how much biosequestration or how much biosequestration we're actually getting. So basically we just multiply the green by the beige, oversimplifying a bit, but essentially we multiply those 2 together and we get the percent of total biosequestration. So if we do that, and then you kind of scroll down the beige column furthest to the right next to the red, it's a little bit smaller on my screen, but it looks like forests were the biggest one. And kind of the medium age forests where we had the most of them, also sequestered the most. So that's kind of a notable finding. We'll come back to that in a bit. And then in the red, we also looked at how much stored carbon was within these ecosystems. So we essentially modeled it for 100 years, 3 generations, figured, that's somewhat reasonable. And we came up with some values of the stored carbon that we'd expect to see in these ecosystems. And we just calculated it a couple different ways, a couple different units. So one was per hectare, and then the other one's multiplied by the green area to see the total amount for this region. So that was the model. It's a bit complicated. I don't need you to understand it all, but I'm gonna walk through the different steps, and then we'll talk about kind of the punchline, help them answer their question of how can they best manage their land to sequester the most carbon, which was kind of the point of the assessment. So we looked at different levers for forests. We looked at different logging practices because a lot of the forests within the land were being logged. But at the same time, our client didn't necessarily have a lot of influence over that, like it wasn't their jurisdiction. Forestry is managed by the province. So we also looked at some other things like development, something that was closer to their jurisdiction. You know, what happens there when carbon gets released? What's the difference between that and forestry? That was an interesting study. We looked at aquatic. There were historically a bunch of kind of salt marshes that had kind of been lost over the years. There's some harbor stuff, development going on. There's some initiatives to kind of bring those back. So we looked at the carbon potential in there. We looked at agriculture. There's lots of opportunities. Like Maria had mentioned in one of her slides, that agriculture was a big opportunity for Southern Ontario. Again, there's a bunch of agriculture in this region. So what are the things that they could do to sequester more carbon during the agricultural practices, and which one had the most potential to store carbon? We called it low veg cover. It included wetlands. So we looked at the wetlands, what was going on. Interestingly, if I'm going to throw back to your slide, she paired really well with mine. So we're on Vancouver Island. We were in the less than 5% of wetlands classification, which aligned with what we found in this specific region, where it really was less than 5% and maybe less than 2%. We had very few wetlands in the region, so that wasn't a big focus for this client, although, you know, it had pretty good potential to store carbon, but because the area was smaller, the overall potential was less. And so here is my favorite pictogram from the project that shows kind of the magnitude of difference between annual sequestration to stored carbon for each of kind of the main 5 ecosystem types that our client had in their region. So like agriculture was on the left, salt marsh, which was like the marshy bits in the ocean were pretty big. And then forests really kind of took the cake in this region. Both the older forests as well as the medium-sized forest. But actually, if you look, I think salt marsh beat out the medium-sized forest in terms of stored carbon, which is an interesting finding, because looking at it, you wouldn't suspect. It just looks like a bunch of kind of rushes or grasses growing in the ocean, but it kind of traps sediment and manages to store the sediment that contains carbon in the root structure, and kind of it keeps growing up as it accumulates. So it actually had quite fantastic carbon storage potential. But if you compare it, and we tried to scale these, actually had to make the balloon of the lighter pink balloon. I guess you can see my cursor there. Just a little bit bigger so you could see it, because it was so tiny. But basically the annual carbon sequestered is quite a small amount compared to the carbon already stored. So that was a important, you know, kind of huge finding, that actually the carbon stored there is so important compared to this sequestration, and that comes out in our findings at the end. So here we're kind of getting closer to the punchline of answering the question, where protection of forests from development, although it may be somewhat of an uncomfortable result because it makes it challenging to manage. You know, people want to develop land, they want to use it. But But developing that land to the state where it can no longer be a forest has huge carbon impacts, and actually the biggest carbon impacts of all the different scenarios that we modeled. So best to know that and go in eyes wide open. And essentially it came out with, one of our most important recommendations was to carefully manage the conversion of forests from development, because that essentially was the policy that would have the biggest carbon impact in their region. In comparison, just to help our client understand the numbers, we looked at what if you protected forests from logging, would it have the same impact? And the impact was only about half, because at least in the logging scenario, the soil is still there and a forest will regrow. So when we modeled it over 100 years, the impact was less of protecting forests from logging than it was of protecting forest development by about half, because at least with logging, the forest, when the forests regrow, it continues to sequester, it continues to build carbon. And so all is not lost, maybe about half is lost when you think about it in terms of carbon. And then the other finding, salt marsh, which had such great carbon potential, and there are already some initiatives underway. We kept that as a key recommendation to essentially restore a bunch of the lost salt marshes from their area, because it had such a great carbon punch. And so those were essentially the two key findings from this study. And so just to kind of wrap it up and summarize, like, how is doing a biosequestration assessment useful? Basically tells you what you have. It helps you understand the carbon in your land. So what sort of ecosystems do you, not just what sort of ecosystems do you have, because you probably have a good sense of that already, but I guess exactly how much of what ecosystem you have and what the carbon value on both an annual sequestration rate as well as from a stored carbon that you have. And with those three pieces together, then you can start to answer more complicated questions like, what can you do about it? What are you doing now? And how does that affect the carbon? And that helps you, make decision in terms of what's gained, lost, and you can put numbers to it and okay, well, if we do this, we're going to save all this carbon. And then, so I think that concludes the presentation. I would love to hear questions. I'm sure all the speakers would. Questions help us know that our presentations were valuable and interesting. So John, I see you popped up. Take it away.
Great. Yeah, right. Thank you, Brennan. Thanks, speakers. Thank you, Shaheen. Thank you, Maria. Thank you, Brennan. Great presentations. Very interesting content.